just talk a little bit about the current state of fusion research. What's been in the news? The National Ignition Facility is one of the two largest fusion programs in the country, in the world. It is a gigantic laser about the size of several football fields. It costs $5 billion, and they recently announced that they would be unable in the foreseeable future to reach their goal, which is the ignition of a single controlled fusion reaction. Another fusion project, which is the largest in the world, is called ITER, which is the International Tokamak Experimental Reactor, which is to be an enormous tokamak device. We'll talk about the tokamak a bit in a second. It's budgeted at something like $20 billion, and it's projected not to do their first experiments until about 2027. So if these projects with billions of dollars have been unable to reach just the first level of scientific feasibility for controlling thermonuclear fusion for peaceful purposes, then why does little Lawrenceville Plasma Physics, our company, think that we can prove scientific feasibility for about $2 million more and get a working prototype fusion generator for $50 million? Are we crazy? Are we just doing something different? Well, I'll let you guys decide by the end of this presentation. So, we talk about sort of our trade name for what we're doing is, we call it focus fusion. And focus fusion means the controlled nuclear fusion, that is the controlled release of fusion energy from the nucleus using a device called the dense plasma focus and using hydrogen-boron aneutronic fuel. So the first difference that we have from what the big guys are doing is aneutronic fuel. And that's an extremely important difference. What this means is that we are using a fuel, hydrogen and boron, that react together at high temperature, briefly fuse to form an unstable carbon nucleus, and immediately break apart into 3 stable helium nuclei with a tremendous release of energy. Aneutronic means no neutrons. That means no induced radioactivity. And that's what makes fission reactors of concern, production of radioactive waste. With this fuel, there is no radioactive waste. The other thing is, neutrons are tremendously destructive of your material structures. Without neutrons, you can make the structures very small, have a very dense energy source. And what that means, if you have small-sized devices, then you can reduce the cost. In addition, you have direct conversion of energy into electricity. What the energy comes out is in the form of moving charged particles. These, do we have a pointer? All right, I'll use my finger. These helium nuclei are charged particles. When you have the motion of charged particles, you have electricity. So you can take the electricity out of the process with a sort of high-tech transformer. You don't need to go the route that we have been going since Edison, which is taking a heat source, boiling water, running it through a turbine, using that to turn an electrical generator. That's what we've been doing for over a century. It's extremely expensive. This is direct conversion, so potentially the costs are much less. The fuel is abundant. Hydrogen, of course, comes from water. Boron is an abundant element. We mine it out of the ground. If necessary, we can take it out of seawater. And, as I said, it's extremely safe. There's no long-term radioactive waste. And, of course, since this is nuclear, there's no greenhouse gases. So that's big difference number one. So these advantages translate into our approach being much cheaper than the conventional approach, both for research and for generators. The FF1 generator cost about $500,000 to build, compared with billions for ITER or NIF. And similarly, if this approach is developed to the point of generating electricity, our approach will produce electricity at about 6 cents per installed watt versus several dollars per installed watt for the conventional approach. Of course, if advanced fuels, PB11, have all these advantages, why do people use deuterium-tritium fuel in the first place? Well, deuterium-tritium ignites at the temperature of 400 million degrees. And that doesn't sound like much of an advantage, except when you consider that PB11 ignites at 1.6 billion degrees, 4 times higher. Therefore, a lot of people have taken the approach, well, DT is easier. But with our experiments, we've already proven in peer-reviewed publications that we can achieve the necessary temperatures to ignite this fuel. So we've overcome one of the main barriers to using what is generally considered the ideal fusion fuel. So the other main difference with our approach is the type of device that we use to burn this fusion fuel. Now the major conventional device is called the tokamak. And this drawing gives you some idea of the size. If you can find them, down in the left-hand corner, there's a little guy representing the size of a man. So this is a gigantic machine. But the other thing is that the approach of conventional fusion is to try and make the plasma stable. It's to try and make the plasma sit still, sort of like a good dog. The problem with that is plasmas don't want to sit still. Plasmas in nature are continuously unstable because currents flowing in the same direction want to attract each other. Currents flowing in opposite directions want to repel each other. So our approach, instead of trying to fight the instabilities, is to use the natural instabilities of the plasma to concentrate the energy, and at each stage to make it more and more dense. So this instability, which we call the pinch effect, which occurs, as I say, when two currents are traveling in the same direction, is a fundamental process throughout the universe. We see it, for example, in the aurora on Earth, the northern lights, where electric currents are coming through the magnetic field of the Earth and coming into the atmosphere and forming these filamentary curtains of light. We see it at a much greater scale on the surface of the sun, where huge filaments like this project vast quantities of matter away from the sun, and actually also lead to the phenomenon of solar flares. And we're seeing one here with the filament of current coming off of the sun. And on still larger scales, on the scale of nebula, these vast clouds of dust and gas between the stars, much larger currents form these filaments that are light years long. And these filaments eventually condense into new stars like our sun. In addition, if these currents are sufficiently dense, then they start to twist and kink themselves up, sort of the way people still have landlines. Your telephone wire used to kink itself up. And what we see here is some of these filaments. This is, over here, this is the surface of the sun. This is the development of a solar flare. And you see how this is becoming a little corkscrew. It becomes a bigger corkscrew, bigger and bigger. And finally, there's an enormous, intense beam coming out of here. This is the process of a solar flare. There's a gigantic explosion that comes out of the instabilities caused when these filaments of current kink themselves up. Again, on a larger scale, stars that are in formation emit these huge beams from the currents that are flowing inward towards the star as it forms. This is a picture. This is several light years long, many, many millions of times bigger than the solar system. This whole thing is called a Herbig-Haro object, which is just a fancy name for a star in formation. This is what the sun looked like when it was becoming a star 4.5 billion years ago. And a still larger scale, quasars, which are gigantic explosions at the center of galaxies, use the same kinking process to send out these enormous beams that stretch over millions of light years. And in fact, it was the study of quasars using the dense plasma focus as a model that actually led me to formulate the theories that I'm now using in the development of this device. And on a larger scale, the formation of the giant spiral galaxies, of which Milky Way is one, again come out of the formation of these filaments. Filaments that, as Carl Sagan might say, carry billions of amps of current. All right, so with that as a lead-in, what is the dense plasma focus? The dense plasma focus is a fusion device. And it is extremely compact. It consists of a set of 2 copper electrodes. This is a used anode, the inner electrode, which will pass around. And we have the cathode bars. What happened to the cathode?
There should be right there somewhere.
Don't worry, it's not. We'll find it.
Yes, it's under that plate. Pick up the plate. Pick up the plate there.
There we go.
So you can just pass these around. So this just shows the electrodes themselves on FF1. And this gives you an idea of the actual size of the entire experimental device. This is FF1 without its vacuum chamber, so you can see the little electrodes right in the center. And the big blue objects are the capacitors.
At the heart of the dense plasma focus are 2 cylindrical electrodes only a few inches across, nested inside each other. The electrodes are enclosed in a vacuum chamber with a low-pressure gas filling the space between them. A pulse of electricity from a capacitor bank, an energy storage device, is discharged across the electrodes. For a few millionths of a second, an intense current flows from the outer to the inner electrode through the gas. Instabilities first compress the gas into dense filaments. These filaments are little whirlwinds of plasma. The sheath of filaments converges together into a dense pinch or focus, combining all the filaments into one. This filament kinks and twists itself into a tiny dense ball only a few thousandths of an inch across, called a plasmoid. Instability in a plasmoid creates powerful beams in opposite directions. Positively charged nuclei flow in one direction, and electrons flow in the other. The electron beam heats the plasmoid to billions of degrees, hot enough to fuse nuclei together to release fusion energy. In sum, the DPF operates by leveraging electricity to induce a plasma state for some gas. It then exploits a series of instabilities within the plasma to bring about controlled nuclear fusion. We call this focus fusion.
So let's go over this again slowly. Basically, the first instability is the formation of the filaments. So the filaments are forming here and are running down the end of the electrode. So that's the first instability. And the second instability is that the filaments merge together into a single filament. And then in the third instability, these filaments twist themselves up into the plasmoid. So this is the formation of the plasmoid. The fourth instability, this plasmoid creates a beam of electrons in one direction and ions in the other, which then heats up the plasmoid to produce the fusion reactions. So that's a series of 4 instabilities, each increasing the energy density. This is an artist's conception of what the generator would look like, with part of the energy coming off in the form of a beam going into the spiral. So the beam goes into this helical coil, which is basically a form of high-tech transformer, which collects the energy into an electric circuit. The second part of the energy comes off in the form of X-rays, which spread out into this onion-like array of photoelectric receptors, which collects the energy and again converts that into electricity. And this gives you some sense of the scale of a generator, which could fit into a garage and produce about 5 megawatts of power, enough for a small community. Thomas Alfvén in 1970 won the Nobel Prize in Physics for his contributions to the entire field of plasma physics. I developed a theory that connected the operation of the plasma focus with astrophysical phenomena such as the quasars. So I had to develop a quantitative theory that projects this natural phenomena from the scale of the laboratory to the scale of galaxies. And we tested that against experimental results. And what that theory predicted was that you had to shrink the whole device in order to make it function well. So we made these electrodes considerably smaller than other such devices. We also developed the idea, and this was a contribution of one of my co-workers, Aaron Blake, of an axial field coil to control the spin, to control how much the plasmoid is spinning and then controls the size. And we can go into this if people are interested in the question and answer. I also applied a known physical effect, quantum field effect, to understand how we can tailor this machine so that the X-rays emitted by the electrons don't cool off the plasma and make it too cool for fusion. So these are various advances that we've had over earlier DPF work. What I want to emphasize is the physics we are using here is not something that's come out of my head. This is physics that's based on the basic 19th century development of the theory of electromagnetism by Faraday and Maxwell and others, 20th century quantum mechanics and nuclear physics, and on research done by tens of groups working with this very device over the last decades. Our experimental program actually started at the beginning of the 1990s, in which we ran an experiment funded by NASA's Jet Propulsion Lab at the University of Illinois, Champaign-Urbana. We had major delays based on funding and inability to get another facility, and we didn't run another experiment until 2001 at Texas A&M, also funded by NASA. And then, unfortunately, NASA was ordered to get out of the fusion business, and our funding ceased until we could raise enough money privately to do this present series of experiments at our own facility, starting in '09. And we're now collaborating with other plasma focus groups, such as Kansas State University and at the Ernst Young facility in Las Vegas. So these are just a few of the innovations that we've made and which are contained in our patent. So where are we? And we'll pretty much get to the question and answer soon after this. Basically, to get net energy out of fusion, you need a tripod. You need three things. You need sufficient temperature. You need to confine that temperature for a sufficient amount of time. You have to have very high density, so the fuel burns fast enough. Well, we've achieved two of those goals. We've gotten over the 160 keV that we have calculated would be necessary to ignite PB11. We haven't done that with PB11 fuel yet. We at the moment are using deuterium, which is simply a much easier fuel to work with, as a bigger experimental base. We should be moving to PB11 very shortly. We've demonstrated the confinement time that we need, which isn't much, 20 nanoseconds, 20 billionths of a second. We've demonstrated we can efficiently transfer energy into the plasma, but we haven't got the density we need. And in fact, we need to increase density by several orders of magnitude. We have a plan for doing that. Now, before I get to that, I should mention, we don't have to entirely take my word for our achieving these extremely high temperatures. We have published this in a peer-reviewed journal, the Physics of Plasmas, earlier this year. So our plan for getting higher density is, first of all, to get greater symmetry of our compression. And that's basically just getting up to speed, getting everything right in putting our machine together. And the machine, even though it's small, has to be put together right. And there's a learning curve. So that's the first step, which is something we intend to achieve very quickly. Second, we get a 10 times increase in density just by increasing the current from our present level, which is about 1.4 megaamps, to our planned maximum of 2.0 with the heavier gas is going to be greater. Now, the goal of our present phase is to prove scientific feasibility, to prove that in one pulse we can get enough energy out so that with reasonable conversion we could get net energy out of a generator. We need a much bigger project. We estimate about $50 million to get net power out. Net power means that we have an entire prototype generator that collects the energy and funnels it back into capacitors. So I don't expect everybody to read this diagram, but this basically shows that we've calculated how much energy is lost at each step, so that with the gains that we anticipate, we can have from the gross fusion energy of 66 kilojoules, a net energy of about 24.5 kilojoules fed out to the grid. In the engineering phase, which we're not working on right now, as I say, would take a bigger effort, we basically see three challenges. One is, like any device, it is going to have some waste heat that has to be removed, especially from this rather small object, the anode. We see basically doing that with compressed helium cooling, which other people are also developing. The second engineering challenge is developing that X-ray onion device, which we have invented, but has to be proven and developed from an engineering standpoint. And the third, and probably least of the challenge, is high efficiency ion beam conversion. There is already megawatt magnetron devices that take energy out of an electron beam at something like 87% efficiency. So we're pretty confident that we can reach the 80% efficiency that we need without stretching existing technology very far. Now, we're not the only group that is trying to do a neutron fusion. To our knowledge, there are two other groups, both of which happen to be also in the United States. There's the Hollywell effort, which is being funded by the Navy, and there's Tri-Alpha, which is basically being funded privately, both of them at a considerably larger effort than ours. This is sort of a comparison where they are in achieving this tripod and where we are. This is putting density and confinement time together as a product. We call it n-tab. And this is a logarithmic scale, so for each of these it's a factor of 10. So this is 10 to the 5th, 10 to the 10th, 10 to the 15th. And this is the log of the temperature scale in thousands of electron volts. The conversion is 1,000 electron volts. It's about 11 million degrees centigrade. So this is where Hollywell is. They've got pretty good temperature, but very low density. Tri-alpha has better density, but pretty low temperature. And we have a range of results from very good temperature, basically what we need, and reasonably good density, to better density and lower temperature. So that's basically where we are. This is where we need to go. And just for comparison, the Princeton tokamak is not even where we are. And they're aiming not for PV11, but for deuterium tritium.
So you need to go to that right, that pine shaped thing, the light
The
explosion.
pink explosion, right, yeah. Now, this is some things that some of our colleagues have said about us. Bruno Coppi is the leader in an effort called the Ignitron, and that's a form of tokamak. So he's investing his career in another horse, but he thinks our horse is worth funding. The second quote is from an Iranian group that is studying similar approaches theoretically, and finally from one of our colleagues in Mexico. Now, people are, of course, interested in how do we protect this invention of ours. We do have intellectual property, which is U.S. patent, etc., and basically it's pretty broad patent. It protects the fact that we've discovered that the size of the device is important. It protects the X-ray capture device. It protects the axial field wall. So it's pretty broad, and it protects it not only for fusion applications, but also for spin-off applications, such as using this as an X-ray source, things like non-destructive testing. We have an Australian patent, which is pretty much identical. And we have patent applications with the same priority date for Europe, China, Canada, India, which are moving along. So what's holding us back? What could make us move faster? Well, there's too few of us, for one thing. I mean, I think we have a terrific team. Right here we have, in this room, we have Derek Shannon, who's been terrific in the laboratory. Ivy Karamitsos, who has been doing many, many different tasks, including working in the lab. Sam's on our business end. We also have Aaron Blake, who's Chief Financial Officer. And off-site, we have my collaborators, John Thompson, who's a plasma physicist who helped to build this device, and John Guillory in Virginia, who's helping us with the simulation of the device, and Dr. Warwick Ma, who's over in England, who's also doing the simulation work. So that's the problem. I'm not forgetting anybody. It's too small a team. What we would really want is another experimental, or a experimental plasma physicist on site. My background is theoretical plasma physics. I've been learning a lot of the details of the experiment as we go along. We need somebody who's very experienced in using this machine. There's a couple of problems with getting somebody like that. You need money in the bank to attract somebody to a startup. And we've been getting funding and spending it as we go along. That's a disadvantage if we want somebody in the United States, who are mostly senior people with their own lab, to relocate to a startup. In terms of younger people, unfortunately, this country has not been training people in this device and not been training them very much in plasma physics. So all our job applicants who are younger are from outside the United States. And that gets us into the immigration mess, which is, as almost everybody I'm sure is familiar with, is very difficult to deal with. Money would help a great deal. We are trying to accelerate things through international collaboration. The Iranians, oddly enough, have the most advanced program in this device, and we recently signed a scientific publication collaboration agreement with Plasma Physics Research Center in Tehran. And yes, this is legal under the sanctions, which have a loophole for scientific publications. In addition, we're trying to involve Japan, which also has an active program in plasma focus. But finances could be improved. We've raised $2.7 million from one institutional investor, Able Foundation, and about 40 private investors, individual investors. We're raising another $1.7 million right now for scientific feasibility and for the transition to the engineering phase. And eventually we'll need about $50 million, we estimate, not necessarily all from private sources, for the development phase. We have an active application with ARPA-E which is the Advanced Research Programs Agency for Energy. And one of their reviewers wrote a fairly favorable review saying that what we did was based on credible prior work and that it would be great if it works. We did hear from them that we had been selected for a callback, and we talked with them by phone, and seemed to have been a fairly promising conversation. On the other hand, they are absolutely overwhelmed with applications. It's an extremely competitive grant program, so we don't have any guarantees. They don't even know when they're going to announce the winners, but they think it might be sometime in next month. Now people say, well, if this is so great, why are we short on funds? Why is there no stampede to invest? And I think stampede is sort of the operative term. We found that there's really is a herd mentality among investors, even, I have to say, among most clean energy investors. You know, there's solar, there's wind, and there's geothermal. And it's very difficult to get people to sort of think outside the box and go with something that's as far in a different direction as what we're doing, even though what we're doing is based on extremely sound physics. Department of Energy is another problem. They focused for the last 40 years on the tokamak as essentially all the eggs in one basket. We're hoping that that might be changing. Recently, one of our new investors pointed out this quote from a recent BlackRock report, which said that they are keeping their eye on startup fusion companies. And as I mentioned earlier, there are very few of us, but it's less than a half dozen such companies on the entire planet. So possibly this will change with our next big results. So that's about it, and thanks for your attention. I've taken up more than my time, but I'm open for questions and answers.
I'd like to add a couple of things as well.
Okay. Do you think we can have a few questions and then?
Well, I want to ask you one or two questions because it might not be clear to everyone. What's the size of the machine going to be?
Well, the size of the machine is what was illustrated in the illustration of the man standing next to it. So
we talking the size of this room?
That's something that would fit in somebody's garage. It won't fit under the hood of your car, but it would fit in a ship or a train if you wanted to use it.
There. Go back.
There we are.
Now, if you have your funding, the $2 million you're asking for, what do you believe is the timeline for feasibility?
Well, I hesitate a little to say timeline because everybody underestimates the deadlines, but we do look to get feasibility within the next 12 months.
Once you achieve the feasibility, then it goes to the next stage, which is engineering. You figure a timeline on that is about 3 to 4 years?
That's right. If we got instant funding, in other words, if the day after we announced our feasibility, somebody said, here's a $50 million check, then we would say 3 to 4 years to actually solve the engineering problems with an adequate program.
Now, an investor that comes in, say with the $2 million, would they have the right of first refusal to go for the $50 million for the engineering?
Well, at the moment, I should say something about our ownership structure. The ownership structure, this is a C corporation with 2 classes of stock. Common ownership structure, such as Google or the New York Times. The Class A voting shares are only owned by myself. Now, this is purely a defensive strategy. We feel that if this technology proves out, we do not want a hostile takeover by, let's say, ExxonMobil. So that's the only reason for that. We have a shareholders agreement, which was created by our first big investors, including Abelheim Corporation, which protects the interests of all of the Class B shareholders, people with the non-voting shares. Among those provisions is that the existing shareholders get first dibs on any share offer. So any share offer that goes out, the existing shareholders can first have their pro rata share. So at the moment, the existing offer, which the existing shareholders